Brian Hentschel from the Harvard University, talking about the column sketches, the scan accelerator for rapid and robust predicate evaluation.
Hi, thank you. So my name is Brian. The work I'm presenting today is column sketches. This is work I did with my lab mate Michael Kessler and my advisor Stratos Adreos. So if we look at some of the ways the world has changed recently, there's been an explosion in the amount of data we have and the performance of our machines. And the result is an increasing number of analyses, from monitoring to complex SQL queries to machine learning pipelines. But in all these operations, an important component is filtering our large data set into some smaller data set that we actually care about. And this is true across a variety of different data systems and a variety of different data formats. So to start, we're going to run through a couple different techniques. The important thing to note here is that while these techniques all have cases where they work really well, they also have cases where they don't work as well. The technique we're going to show today works fairly well across all cases and is the best for some of them. So we'll start by looking at traditional indexes versus table scans. And traditionally, we've always had a selectivity crossover where our scan becomes better than our index. And this has dropped over time. And a recent paper from our lab showed that the crossover is about 1% as of last year. And we're going to be focusing mainly on this area here, the area above the selectivity crossover. If you're going to select only one tuple, there are better indexes than column sketches. So why have scans gotten faster? And the first is the change to columnar layout. But just as important are the fact that we have data parallelism and task parallelism. So data parallelism is our SIMD or our GPUs, and task parallelism is our multi-core or multi-machine. So we ran a query on our lab machine at around 3% selectivity, and we found that our scan was about twice as fast as our B-tree. We're next going to go through two techniques to speed up scans. The first is zone maps. And zone maps and their variants all work by having summary statistics for groups of values. So you see here they're storing just the min and max for a range of values. When items' positions are correlated with their values, for instance, shipping dates tend to come in order, this is very effective because you can get a range query, you look at this simple amount of metadata, and you prune almost everything, seeing only a small amount of the data. But this is only useful when position and value are correlated. If they're not, what ends up happening is this metadata is largely useless. So if you have account balances, these don't generally tend to be correlated, and so you scan everything. The final technique, so you see in our example query, this is exactly what happened. So our scans with zone maps are not really any faster. The final technique we're going to talk about is early pruning techniques, which I think of as bit weaving and byte slicing, as well as a couple other variants. And they all work in mostly the same manner. They partition by bits, and then they conduct predicate evaluation from the high order bits to the low order bits. And they're going to be able to say that things are evaluated when they're no longer equal to the predicate value along these high order bits. And the predicate value is something like 100, and the term x is less than 100. And then you need some groups of values to be evaluated before you can actually skip data. So what can go wrong in this case? The problem is that you might have something like this, where your distribution has heavy left skew. And so your high order bytes aren't uniformly distributed, and in fact, they're almost always low. So if you query in this region, what happens is that, like, let's say you're looking at something that has 1 on the high order byte. This matches some of the values in a group, and so you end up looking at the low order bytes. And so eventually what happens is your performance degrades to your regular scan. And this is true as well for heavy hitters. So in this case, we're looking at customer cities. We have Los Angeles and New York, which have been dictionary encoded. These values are going to appear a lot in the high order bytes. So if you're looking for them, it's going to match somewhere, and you end up looking at the low order bytes. And so for these distributions, these early pruning techniques end up looking like traditional scans. So that's what happens here. We have values skewed toward the low numbers, and so bit weaving also looks like a traditional scan in this case. So we want something that's going to work across a range of different scenarios. And to do this, we're going to create a function S. And this function S is going to do 3 things. The first thing it's going to do is perform lossy compression. The second thing it's going to do is make our data look approximately uniform. And then finally, while it makes the data uniform, it's going to identify the heavy hitters. And we'll get into why these are all important as we go along. So there are also a couple things that we're not going to talk about, but I do want to highlight very quickly. The first is that column sketches tend to have low memory overhead. The second thing is that they can actually easily be integrated into systems. And the third thing is that they can ingest data fairly quickly. So this is the basic view of a column sketch. The first thing to note is that column sketches are a secondary index. They're auxiliary to your base data. There are two components. In the middle is the compression map, which is this function S. And the second thing is the sketch column. And the sketch column is built by feeding values in from the base data on a value by value basis and applying S to them and then writing them out to the sketch column. And then this function S is what has all the properties that we want. It's what makes the data uniform and performs lossy compression. So let's go over a quick example of how to query a column sketch. If we look at the predicate p equals x, we can feed this predicate value p into the function s. We look at the result, and then we can scan the sketch column, checking if s of p equals s of x for every value. If these don't match, x can't equal p. If they do match, we're not certain, so we go to the base data. And we want to bound the number of times we're going to look at the base data. So let's look at a more detailed example. Here's our base data on the left. In the middle is our compression map. I currently want you to take this function as just appearing from nowhere. I'll tell you how to build them in a little bit. And then on the right is our sketch column. So we build this value by value. So we feed 13 into this function. The function is going to look for the first value greater than its input. So in this case, 13 is less than 60, and we write out code 00. And so that ends up in the first position on the right. Similarly, if we feed in 191, 191 is between 173 and 256, and so this gets code 11, and that appears in the second value on the right. So a couple things about this function s. The first, the function is order preserving. So s of x less than s of y implies the values in the base data have the same order. The second thing is that the function produces fixed width codes, and this what allows data parallelism and task parallelism. And then the final thing is that the sketch column uses implicit identifiers. So the sketch column is positionally aligned with the base data, and so we don't need to store secondary identifiers. This is in contrast to something like a B tree, where you sort by the domain, so you need to reconstruct the positions. And this is what allows the column sketches to have low memory as well as lossy compression. So as well, this column is much smaller than the original base data. So we're now going to look at conducting a range predicate over a column sketch. Here we're going to look at x is less than 90. You feed 90 into the function s, and you check the code value is 0, 1, between 60 and 132. We then scan the sketch column, and we have two cases. Things qualify if they're less than the code value 0, 1 with certainty, and then we're uncertain if we see this code value 0, 1. So you see when we scan, the values 13 and 56, which were assigned code 0, 0, for sure match. We're uncertain about the fourth and fifth positions, and so we go to the base data, and only position 5 qualifies. Position 4 does not. And what we see is that in this case, we go to the base data for every 1 out of 2 to the b values, where b is the number of bits for each value in the column sketch. So as we increase the number of bits in the column per value in the column sketch, we're going to go to the base data exponentially less frequently. So now let's talk about creating that function s. We want 3 things to happen. I'm going to argue that the first basically just happens naturally. So we have some input domain. We just create an output domain that has smaller cardinality, and therefore you have to perform lossy compression. Done. So now let's talk about creating data uniformity. So this is a theorem from probability. It's called the probability integral transform. It says essentially let f be a CDF, so let f be any distribution, and sample from that distribution. If we apply the CDF to the sample, we get something out that is uniform. And so this is going to give us the intuition for how to build the column sketch. We're going to create that CDF. How do we create the CDF? We first sample from the distribution. We then sort the samples. And then finally, we inject breakpoints. So if we want 2 codes, we inject a breakpoint right in the middle. If we want 4 breakpoints, we inject at the quadrants. And generally, if we're going to want more than 4 codes, and we're going to sample more than 8 items, but this is going to be the general procedure. So the first question is, how many samples do we need to take? This is going to be something called the Dkw Inequality. This thing highlighted in red is the thing we care about. It's bounding the distance that our sample CDF is away from the true CDF. And it's doing this for all values in our domain at once. The second thing to note is that this is for all distributions F and for all data sizes M. And actually, neither of these 2 terms appears in our bound. So our bound is independent of both of them. And what this essentially says is that regardless of our distribution, the chance that our estimated CDF position is far away from the actual CDF position is exponentially unlikely as we take more samples. So I actually glossed over this word continuous, which is in the probability integral transform. So our input domain is actually discrete. It's not continuous. Can we still build good functions? So this is a theorem from our paper. It says let X be any domain and Y be any domain of size n. So if we're going to choose an 8-bit column sketch, n would be 256, or 2 to the 8. We can build an order-preserving function, S, from our input domain to this chosen output domain, such that for each code, one of 2 things is going to happen. The first thing is that code is going to be assigned not that much of the base data. In particular, it's going to have less than 2 over n of the base data. So in this case, less than 1 over 128. The second thing that might happen is it might have more than that, but our function only assigns a single value of our input domain to this value, to this code. And this is going to make it so we actually don't need to go to the base data for these values. The final thing I'll note is that X can actually be a compound space here. I didn't require that it was a single attribute, so you can make it city and job title together. But the more important thing is that there exists a good function, regardless of what X is. And so between these 2 theorems, we basically have that there is a good function and that we can build this function efficiently. So I now hopefully have convinced you that we can make the data approximately uniform, and I've alluded to the fact that we're going to capitalize on these heavy hitters. So how do we handle this from a mechanical standpoint? This was our original column sketch. This is our new base data. It has a heavy hitter 0, which appears quite frequently. We're going to build this map in the same way, but this time when we sample, we notice that 0 is frequent, and so we just essentially have the map store that there's only a single value assigned to this code. And then we write out the sketch column as usual. What happens when we query on this value is that, so let's say we have the predicate x equals 0. We run 0 through our function s, and that has the code 0, 0. But now we know when we scan our sketch column that the code 0, 0 is for sure the value 0. And so we actually don't need to check the base data at all. And this way, we actually have faster performance when we're evaluating a heavy hitter than when we're evaluating an infrequent item. And so this, I would say, describes what we want out of our function. I'm now going to talk about modeling and when column sketches are useful or provide performance benefits. So we had this slide here, which said we went to the base data for every 1 out of 2 to the b items. So when we look at the actual data movement using a column sketch, we have 2 things. We scan our column sketch, and then we have skip sequential access into our base data. So how much of our base data are we actually going to touch? So the first thing I'm going to introduce is 3 parameters. The first 2 are the size of the codes in the column sketch and the size of the base data elements. These are now in bytes, and they're no longer in bits. And the third thing is memory granularity, which I just think of as a generalization of page size and cache line size. It's the minimum amount of memory you can grab from that level. This is the equation for how many bytes we're going to touch per value in expectation. It consists of 2 things. The first thing is the number of bytes in the sketch column per value. You're absolutely going to touch this no matter what. The second thing is the number of base data bytes we touch in expectation. And the most important part of this is this term right here, which is the chance that a binomial distribution equals 0. So each coin flip in this binomial distribution has really low chance of succeeding. It's 1 over 2 to the 8bs, which means that as we assign more bits to the column sketch, this becomes exponentially less likely. The second term is the amount of coin flips we need, and this is the size of our memory granularity divided by the effective size of our base data elements. So we'll first look at a couple examples for in-memory. So if we have 4-byte integers and a 1-byte column sketch, we end up seeing 1.24 bytes per value for the column sketch, and we see 4 bytes for the regular integers. If we move to 8-byte integers, the column sketch scan still sees only 1.24 bytes, but the regular scan doubles its data movement and so sees 8 bytes. So the next question I want to ask is kind of what happens as we move to persistent storage, and so what happens as we move to flash or disk. So the first thing that's very clear is our memory granularities are going to get much larger. They're going to go from 64 to something in the thousands. So the second thing I want to ask is what happens to the effective size of base data elements. So previously, I kind of assumed things were in column store format. If we move to row storage, the effective size of the base data elements is the size of the rows, not the size of the columns. And so you need many less coin flips to succeed. And this is true even if you're storing something in like PAX or Parquet format, where you're horizontally partitioning by rows before storing things in vertical column format. From this high-level perspective, you're still trying to skip rows of data and not columns of data. So I would argue that this generally goes up. The other thing to note is that you can just increase the number of bits in the column sketch. So you can go from 8 bits to something like 12 bits, and this goes from 1 every 256 values to approximately 1 every 4,000. So we're going to look at experimental results. These are all going to be for in-memory column stores. So this is 4-byte uniform integer data, and we're making a 1-byte column sketch. So the column sketch is about 40% faster than bit weaving, and it's about 3.5 times faster than the optimized scan. If we move to 8-byte data, bit weaving and column sketches don't move, so the column sketch is still about 40% faster than bit weaving, but now it's about 7 times faster than the optimized scan. Now, if we go to skewed distributions, like promised earlier, bit weaving kind of has a degradation in its performance. It actually loses half of its speed up. In contrast, column sketches have the exact same performance, really no matter what the data distribution is. And the final thing is basically just a sanity check that we want to do variable length string data or dictionary encoded string data. And these graphs look basically identical. It's now that column sketches are still about 40% faster, and they're now about 3 times faster than the dictionary encoded data. Thank you. So this is column sketches. It's robust, performant, and low memory.
So question one is like, what's the difference between this and column imprints?
Yeah, so column imprints, so I'm going to go all the way back to my zone map slide at the very beginning.
I mean, I know the difference, but like, what do you think is like the value that you're adding on top of column imprints? That's essentially my question. I know what column imprints does.
So the difference between column imprints and column sketches is that column imprints is still building summary statistics and evaluating groups of data at once, right? So they're building histograms essentially, and then they're marking all the bits.
Yeah.
And so this means that if you're mixing values which qualify and don't qualify, that you look at the base data. And so this is why once like the selectivity reaches like 2%, column imprints doesn't tend to help you. But at the same time, if your selectivity is low and data has some ordering to it, column imprints will give you like an 100x improvement, where we're never going to give you 100x. We're going to give you something 3 or 4.
So the second thing is like you're doing the distribution, which, by the way, is actually also similar to sample sort, like you want to look it up. The interesting thing is the problem there is like that you're doing the CDF with only one part of the data. Say that I have like 100 gigs in my table and I do the distribution, I decide the delimiters there. right? And then I ingest another 300 gigabytes, and those new 300 gigabytes have a completely different distribution.
Yeah,
right?
so that's true. There is the question of like what happens if your distribution changes. So we actually do talk about this in the paper, and so most of the details there. But the main intuition is that your distribution can't change like that fast. So if you have 100 million items and you insert one item, like that can't change the distribution too much. So you need some new amount of data before this can get like truly off. And so then the second thing is kind of how to re-encode the column sketch and write it out. And the good news is because column sketches are a secondary index, you can basically do this in the background. It's not like an online thing like dictionary encoding where you have to do it now. There's a couple more details in the paper, but I think that's all I have time for.
You have time for questions?
Okay.
I know your lab works on LSM as well. I was wondering if this work can be expanded to LSM trees as well.
It might be. I'd be interested in doing it, but the truth is I don't know right now.
It never came up in your lab? How about LSM?
It's a good question. So it has recently come up for whether it can be used for LSM trees, and in particular I was talking to a lab mate about like maybe time series, but the answer is yeah, we need to explore. Thanks.
Okay, let's